topic is Hebbian-based principal component analysis. Now, this primarily follows from one of the very important results that we had presented without giving the proof. That is to say that in order to realize a principal component analysis, computationally, rather than going in for the classical mathematical way of solving the eigenvalue problem and then finding out the corresponding eigenvectors to it and projecting the input vectors into those eigenspace. The same computation can be achieved by using a single neuron, which does, which is based on a Hebbian mechanism of learning. So Hebbian mechanism of learning, as you very correctly can recall, that it says that if the presynaptic signal and the postsynaptic signal, they are correlated, if they are both of the same sign, in that case the synaptic weight has to be updated, increased in that direction, so that next time when the same condition occurs, then with a greater strength it can achieve the same result, the presynaptic and postsynaptic conditions. So, a single neuron can basically do the, basically compute the principal component analysis of the first component. And first component means that if we are arranging the eigenvalues in the decreasing order, then the highest eigenvalue that results, we call it as lambda 1, and corresponding eigenvector we call it as the Q1 vector, and it is the projection of the x vector into the Q1 vector which we are referring to as the first principal component. Now, first principal component can be, as we say, it can be computed using a neuron, linear neuron that works on the Hebbian learning mechanism. And here what we are trying to do is that just to extend that concept into the first L principal components, because essentially that's what can lead to some practical applications for us, because nobody will be interested in knowing just the first principal component alone, although that is the most dominant one, but in a very typical problem where there is a data reduction, now certainly one would like to keep some amount of data at the output also. So, if we have got m dimensional input, we are looking for an L dimensional output where L is less than or equal to m, but certainly we do not want L to be equal to 1 exactly, because 1 is too much of a reduction. So, we want to keep some. That means to say that whatever solution one can achieve using a single neuron, one has to extend that so that the first L principal components could be extracted. So, to do that we have to use a network of this nature, where at the input we will be having m number of inputs basically at the input layer. So, we mark these inputs as x1, x2, x3 up to xm, so that together they will form an m dimensional x vector, and let us say that we have got L different number of computational units or neurons. So, we are taking L of them, so that we will be generating L such outputs from those neurons. So, we will be having y1, y2 etc. up to yl as the output, and our L is going to be less than or equal to m, typically less than m only. That is what we will be having if we are going in for a data reduction. So, now what we have to do is to make the connection from this input layer to the output layer. Okay. And it should be typically fully interconnected type of a network, okay, I mean between the layers, so that what we will be doing is just to connect all these X inputs, okay, to each of these neurons. So, we will be having M connections like this, okay. Again very similarly we will be having M connections for the second one. Like this we continue, and M connections for the last one. All right. And since all the neurons, they are linear, okay, so this is basically a single layer. So, you can see that we are using a single layer of neurons, okay, and the output of those neurons, okay, could be written like this, that if we are considering the jth neuron output at the iteration number n, okay, so we are representing that as yj of n, okay, indicating that the suffix j is the jth neuron, and this n, the number written in the parenthesis, is the iteration number, okay, the iteration of learning. So, this yjn would be in the expanded form written as summation of I is equal to 1 to m. This corresponds to all the inputs, and it will be the summation of wji at the nth iteration. So, basically the weights, the synaptic weights are actually arranged in the same way. That means to say that when we are taking the jth neuron over here, then by wji we will be referring to the synaptic weight connection from this jth neuron at the output, I mean between the jth neuron of the output and the ith input to it. So, it is wji xi of n, right. So, it is a linear neuron model. So, what we have shown is a linear neuron model. Now, in this case what happens is that the synaptic weight wjin, that will be updated in accordance with the Hebbian learning mechanism, okay, because we are all the time assuming that the learning mechanism that we are following is Hebbian learning. Okay. Now, in this case what one has to consider is that if you are considering the output of the, I mean if you are considering the synaptic weight updating of wji, okay, that means to say that whatever is connected to the jth neuron, okay, if you are considering, then all the synaptic weights that are connected to the, I mean that are connected from the ith input to the neurons which are previous to this G, okay, the earlier to those G, that is also to be taken into consideration, because what happens is that, you know, Hebbian learning is a mechanism of a positive feedback type. That means to say that you can imagine it like this, that since it's a combination of the presynaptic and postsynaptic weights, so x1 and y1 together activating actually strengthens w11, okay, and again since that strengthens y1, okay, so that's why when you are considering x2 with y1, the connection of that gets, the w21, it gets altered, and accordingly what happens is that one can formulate a generalized Hebbian algorithm. Okay, now we are not going into the detailed analysis of the generalized Hebbian algorithm, okay, but I am just presenting you the result of the generalized form of the Hebbian learning. So, what we are writing now is a generalized Hebbian algorithm, and In the short form, it is written as GHA. Okay. And according to GHA, okay, the change of the synaptic weights, because here we are taking the jth neuron output. So, we will be interested in finding out that what is the delta WJI, the change of synaptic weight. So, according to the generalized Hebbian algorithm, okay, the change of weight, that is delta WJI for the iteration n, would be written as eta, eta being the learning rate, multiplied by, okay, I mean we did not write down one thing, I mean for the sake of completion we should have written down here that this neuron model, okay, should be followed for all the j's, that is to say for j is equal to 1, 2 up to L, because here there are L. And in this case the equation that we are going to write will be equal to eta times yjn. I mean had it been a single neuron, we know that we would have considered eta yjn xin, okay, but according to the generalized form of Hebbian learning, this is not exactly xin, we have to write it as eta yjn xin, but from this we have to subtract a term which is given by the summation for k is equal to 1 to j wki for iteration n yk of n. So, have you followed what we have considered here? You see, if you try to interpret it, you are considering the jth neuron, all right. Now, jth neuron and I mean jth output and ith input, okay. So, for the ith input, yes, this xi of n is the term that is contributing, but apart from this term, okay, there are some other terms which will be having its effect. And what are those terms? Basically, they are the summation of wki yk. Now, this wki yks will mean that we are considering the kth output and summing it up for k is equal to 1 to j, and k is equal to 1 to j means that whatever has already occurred, okay, for this. So, I mean all the previous yks are being taken into consideration because they will be accordingly, I mean modifying the effective xin. So, this thing can be regarded as the effective xin because of all the contribution of these terms, okay. And here in this equation our I will vary from 1 to m, okay, and our j, the output index, will vary from 1 to L, okay. So, this we are calling as equation number 2, and the first one that we had got, we are calling that as the equation number 1, right. So, this is the change of the synaptic weight that we are going to have, right, and we are just going to write it in a better form, okay, in the sense that instead of writing it like this, let us write this equation number 2 in this way. Wjin will be equal to eta yjn, and let us define a quantity xi prime n, okay, where basically this xi prime n we are defining as xi n minus summation k is equal to 1 to j minus 1, okay, means all the previous, in fact this includes j, mind you, here this generalized Hebbian algorithm that includes this jth term, whereas what we are considering as the definition of this xi prime n is that it is xin minus k is equal to 1 to j minus 1. So, we are going 1 before, okay, wkin yk of n. So, if we define the xi prime like this, all right, then we will be left with some other term over here. So, what will be after this? What will be xi prime n minus obviously, because all these terms are minus wjin yjn. Yes. So, what we are essentially doing is that we are separating out the j related term, I mean the jth neurons term, we are just separating out of this summation, and all the other things we are embedding into the definition of this xi prime n. Okay. And in fact, this itself is acting as the modified input, or so to say xi prime n minus wjin yjn, this entire term that we have written within this square bracket, okay, that is basically serving as the modified input term. So, we can rewrite this equation, okay, call this thing. So, this also is for I is equal to 1 to m and j is equal to 1 to L. So, this we call as equation number 3. Okay. So, equation number 3 can be rewritten as delta wji n equals eta yjn xi double prime n. So, now you get your very familiar Hebbian learning term, okay, and here what is this? This xi double prime n is equal to xi prime n minus wjin yjn. So, basically what we have done is that the term that is written within the square bracket, it is being substituted by xi double prime n, which we have just now defined. So, this being the modified input, the delta wji is equal to eta yj xi double prime n. Okay. So, this will be the situation, okay, if we are looking for a generalized Hebbian learning, where we will be having I mean L inputs and M inputs and L outputs. All right. Now, this computation, okay, in fact can be depicted in the form of a signal flow like this. You see that if we want to get the first term in this expression, I mean we have to of course start with xi of n, right. So, we have to start with xi of n, I mean considering the ith input, and for and from xi of n we have to basically subtract all these j minus 1 terms, okay, that is coming out. So, what we have to do that at first we have to subtract for k is equal to 1 term. So, what we have to do is that from xi we have to first subtract w1i n and y1 n, I mean w1i n multiplied by y1 n, and this we have to subtract from xi of n to start with, and then we get a result. Okay. The difference of that, from that we will be substituting the term w2i n y2 n. From that we will be subtracting w3i n y3 n. So, it will follow in a flow like this. So, this equation, okay, this equation, let us call it as equation number 4. We can represent this equation 4 in the form of a signal flow graph, and the signal flow graph for us would look like this, that we will be taking xi of n, okay, and then from here we will be first subtracting the term w1i of n, and this is to be multiplied by minus y1 n. So, this will lead to the I mean first subtraction. So, we get the first subtraction result, okay, the first term subtraction corresponding to k is equal to 1, and what we get here, from that we have to subtract W2in, and this is to be multiplied by minus Y2n. For the other inputs it continues like here it will be Wj minus 1 comma I n. Okay. So, all the j minus 1 earlier neurons responses we are considering together. So, here this will be minus y j minus 1 n, right. So, again I mean you can verify that all that we have done is the computation of this term with respect to equation number 4. So, with respect to equation number 4, all these j minus 1 terms are getting computed and in effect here what we are having, because already xin has been fed over here. So, we are getting the xi prime n computed out of this signal flow diagram that we have drawn, all right. And from here what we have to realize is xi double prime n, because xi double prime n we have said that it should be equal to the xi n minus wgi n yj n. That means to say that from here we have to subtract another term, and that is wgi n yj n, and it is being substituted subtracted here. So, what we have is that we are just drawing the signal flow from here. So, here mind you we have to give an arrow, and here we will be having wgin, all right, and this to be multiplied by minus yjn, and then if we are subtracting this from this term, that is xi prime n, we will be getting here what? Xi double prime n, xi double prime n, and then we can see that xi double prime n, if we are multiplying by eta yj, that should lead to delta wgin. And what is delta wgin? Delta wgin is nothing but wjn plus 1 minus wgin. Okay. Now, we already have wgin over here. So, what we do is that from this we take this as the connection. So, this is wgi n plus 1, in fact wgi n plus 1 and wgin will be related by this, by 1 unit delay, because if you introduce 1 unit delay between this and this, then what results is basically from wgi n plus 1 we can get wgi n, by introducing the delay. So, that is the relation between n plus 1 and n, but what we are doing here is that we are subtracting wgi n from wgi n plus 1. So, in effect we are getting delta wgi, and this delta wgi is what we are getting from this xi double prime n multiplied by eta yj n. So, this is the signal flow graph, okay, of this equation. The signal flow graph of equation 4 is obtained like this. Okay. Now, once again I repeat here, okay, in case you have any difficulty in appreciating what this generalized Hebbian algorithm has to tell us. Now, we have this delta wgin eta yj xi n, this equation is very familiar to us. We had already seen that in the case of Hebbian learning, but mind you, there we were considering only one output, okay, whereas this one is generalized into, here the Hebbian learning mechanism has been generalized into more than one outputs. Okay. So, this form we just accepting, okay, since we are not going into the detailed mathematical analysis of how it is being derived. Okay. I only try to explain the things, I mean in a more subjective fashion without going into the analysis part of it. So, this flow basically realizes the equation that we were describing, okay. But what is going to be interesting to us is that to show that this network is actually extracting the principal components, okay, one after the other. That means to say that if we take the first neuron, that will extract the first principal component, the second will have the second principal component, and like that. So, we can show that, okay, in a very simplified manner. So, before we can show it, let us try to rewrite this equation number 3. This equation number 3 will be defined for I is equal to 1 to m and for j is equal to 1 to l. So, if we repeat this equation number 3 for all these i's, that means to say that if we write down m such equations, okay, then what results is that we will be having wj1n equal to this, wj2n, like that we write m different equations, and writing those m different equations would be equivalent to expressing that in a matrix form. So, what we do is that in the form of matrix we will now represent this equation number 3, okay, taking the expansion of j into consideration. I mean that means to say that we will now be defining wj1, wj2, I mean delta wj1, delta wj2 up to delta wjm, and together we will be calling that as delta wj vector, okay. So, the matrix form of equation 3, the matrix that can be written as delta w j n, and this is equal to eta y j n and x prime n. I mean if we write it in this form, not equation 3, let us write it in the form, yes, in equation 3 only we have got x prime term. So, it will be x prime n again defined in the form of vector, because this is xi. So, we have to consider I is equal to 1 to m. So, this becomes xi vector minus this becomes, you can see, eta yj square, okay, eta yj square, and wjn will again become a vector, okay. So, this is equal to minus eta yj square for iteration n wjn, okay, and this is for j is equal to 1, 2 up to l, where in this equation x prime n as a vector is equal to the definition of equation number 4 we can simply apply. Again this equation number 4 also is to be written for all the i's. So, this is valid for I is equal to 1, 2 up to m. So, we can write this equation number 4 in the matrix form as xi prime n vector equal to x vector minus summation k is equal to 1 to j minus 1 wk vector ykn, okay. So, this is the matrix form of this equation, and now we can make the following observations from this equation. I mean if we call this as equation number, can we call it as 5? Yes. Yes, correct. Thank you for pointing it out. And now we can make some observations out of equation 5, observations from equation 5. Okay. Let us take the first neuron. Okay. So, for the first neuron, the index j that we have to consider is j is equal to 1. So, we try to write the G equal to 1 case. Now, J is equal to 1 case will be of course, delta W 1. Okay. So, delta W 1. So, delta W 1 of n can be written as W 1. I mean, we are not writing 1 because we are considering only this J is equal to 1 case. I mean, we could write, okay, I mean, if you want, we can write W 1 delta W 1 n. Okay. Now, delta W 1 n will be equal to, I mean, let us write down this thing first. It is equal to eta y 1, okay, x 1, I mean, x prime n, okay, and then we have got what, minus eta y 1 square w 1 n. Now, instead of w 1 n, we can write as w n. Okay. So, we interchangeably write w n for w 1 n, and then since it is delta w 1 n, this is one and the same as saying that it is w 1 n plus 1 or w n plus 1 minus w n. So, if we write down this for w 1 n, then what results is as follows. We can rewrite this as w n plus 1 is equal to w n, okay, plus, I mean, that means to say that this minus this is delta w, okay, delta w n. Okay. So, what we are doing is that this is equal to this eta term. So, after eta we were having lot of terms, eta, now we are going to call this as eta y. So, instead of w 1 n, we are calling it as w n, and instead of y 1, we are calling as y. So, this whole thing can be written as, I mean, here also we should have taken eta, yeah, y n. So, this can be written as eta y of n, and then within the bracket we will be having x prime of n, okay, minus y n w n, right. So, this is this. So, that our w n plus 1, I mean, simply substituting this, I mean, simply bringing this w n term from the left hand side to the right hand side, what results is w n plus eta y n, and within the square bracket we will be having x prime n, yeah, x prime n minus y n w n. Okay. So, this is the first neuron, okay, and in fact, this can be proved. I mean, in fact, I was yesterday referring to Oja's result, Oja of I mean, the paper which he published in 1982. Now, according to his result, he has proved that this neuron, okay, will extract the first principal component. So, this neuron will extract the first principal component. Okay. So, if that is the case, then I mean, assuming that the first neuron has already extracted the first principal component, then for the second neuron, okay, we can see that what happens, what is the thing that the second neuron extracts. So, for the second neuron, obviously, there we have to take j is equal to 2. Okay. And if we take j is equal to 2, then we can see that we have to take this as x prime n, okay, for the second neuron will be equal to x of n, and from there we have to subtract w 1 n y 1 n. Okay. So, the term that we have already considered. So, there basically what we have to do is this minus this has been already accounted for the first neuron. So, that will be our x prime n for the second case. Are you getting it? You consider j is equal to 2. Okay. Again, look at the equation number 5. You consider j is equal to 2. J is equal to 2 means that you are getting W2n plus 1 minus W2n, okay, and that becomes equal to eta y2, okay, eta y2n, and then within the bracket we will be having the term as x prime n minus we will be having this for I mean y1n w1n term will remain, and then there will be minus y2n wn. So, we are considering that the new expression for x prime n for j is equal to 2 is this term, from which we have to subtract y2n wn, and y2n wn is the thing which we are now going to refer as the new yn wn. Okay. I mean anybody having any difficulty in following the result? See, from here we just have to subtract this term. So, if we consider x prime n minus w2n y2n, then that is the same thing as this term. Okay. So, here the new x prime n is becoming x of n minus w1n y1n. Okay. So, what is this? This is the case that from the input vector, I mean this x prime n is basically realizing an input vector from which the first eigenvector of the correlation matrix has been removed. Because we are taking this result that this neuron has already extracted the principal component, first principal component. So, that means to say that x prime n now becomes a modified input vector from which the first principal component has been eliminated, or rather to say the first eigenvector of the correlation matrix has been removed. Okay. So, x prime n, our new x prime n for the second neuron, okay, is basically the input vector minus the first principal component already taken out. All right. So, now this modified input vector will be applied on this algorithm again. So, what we will go through now is simply w2n plus 1 will be equal to w2n plus eta y2n x prime n is this one minus y2n w2n. Instead of 2 you can write it as y and w, instead of y2 and w2 you can write as y and w, because we are interested now in extracting j is equal to 2. And what will it extract? It will extract the first principal component of x prime n. Earlier it was extracting the first principal component of x n, okay, and now it is going to extract the first principal component of x prime n, okay, and first principal component of x prime n means that it becomes a second principal component with respect to the original, I mean with respect to the original vector. So, here this neuron will extract the first principal component of x prime n, okay, which is equivalent to the second principal component of the original vector x n. All right, and now we can continue this iteration. So, if we now take the third neuron, so for the third neuron, definitely we have j is equal to 3, and there what will be x prime n? What will be the x prime n for the third one? Anybody can suggest? The first two terms will go away from the x n vector, right? So, x prime n will be, yes, equal to x n minus w 1 n y 1 n, correct, minus w 2 n y 2 n. Okay. So, from the third neuron, so that means to say that this will extract the first principal component of x prime n, equivalent to second principal component with respect to the second neuron, or rather to say the third principal component with respect to the original. So, this extracts the third principal component with respect to original. Okay. So, this way we will continue up to all the L. Okay. This is one way of showing that we are considering one after the other, but that does not make this algorithm sequential, mind you. I mean, it is only for the ease of the analysis that we have shown it like this, that considering the first one to have already extracted the first principal component, how the other neurons extract the in the same way the second one, third one, like that we had shown in a step, but everything can be trained together. So, when the network having L neurons, okay, will be trained by a Hebbian mechanism with sufficiently large number of n, okay, in that case that will ultimately evolve into the extraction of the first L principal components. And this kind of a mechanism, will you call it as a supervised or an unsupervised? Definitely unsupervised, because we are not feeding any target output for this. Okay, we do not have any desired or target output for that, and basically what we are doing is that we have to keep on feeding the different input patterns. Okay, we have to feed various examples of this x n vector, okay, and if you feed all these different examples of x n vector, then the network will train up finally, train up in the sense that it will be finally able to extract the first L principal components. And this has got a very wide application. So, I can make a mention about the image coding application where the principal component analysis can be employed. So, primarily what you need to do is that, supposing you are given with an image, let us say some image of a fixed size. Let us say that you have got 256 by 256 pixels of the image. Okay. Now, what you can do is that this image you have to represent in fewer number of bits. Okay. That means to say that you have to achieve some data compression out of it, because if you look at the original image, then it will be containing 256 by 256 number of pixels, and even if you consider it to be a grayscale image, then it will be 256 by 256 by 8. Those many number of bits will be required to represent that. Now, what you can do in order to achieve data compression is that you can divide this 256 by 256 into some non-overlapping blocks, into non-overlapping blocks of 8 by 8 or some size like that. I mean, let us say that we subdivide the image into non-overlapping blocks of size 8 by 8. Now, 8 by 8 basically corresponds to 64 inputs, I mean 64 pixels. So, considering those 64 pixels as the input, okay, we can train up a principal component analysis network, or rather to say a neural network like this, which will be having 64 inputs and less than that number, I mean our desired number if we want, okay, those many number of outputs we will be having. So, if we train it up with sufficient examples of this 8 by 8, in that case the network will ultimately extract the first L principal components of that, and the first L principal components that we are getting will represent the original 8 by 8 block. So, like that every block can be transformed into a block of to a data space which has got a dimension less than that of 64. In this case it is 64. So, we are going to project it into a space and we are going to get it less than that of 64. Okay. And then if we apply the reverse transformation, because we know that how the synthesis also can be carried out, the synthesis also can be done using the neural network structure with Hebbian learning, and then we can obtain the reconstructed image back. Okay. It is the same encoder and the decoder mechanism that I was telling you in the last class, that where the encoder will represent it in a fewer number of samples as compared to the original input space, okay, whereas the decoder will restore it back. Okay. Only thing is that the decoder will not be able to restore it exactly, because we have already decided to chop off some of the chop off the data in the projected space. Okay. And projected space truncation of the data will not contribute to much of an error, because we have projected it into a space so judiciously that only the low variance terms are eliminated. Okay. So, that is essentially the purpose and the use of the principal component analysis, okay, and neural network with Hebbian learning mechanism, okay, contributes to a better practical realization of the principal component analysis. Okay. You have got any questions? Okay. If there is none, then we can stop it for the day, and then we will be taking up the next topic as a competitive learning mechanism, which is the self-organizing map. Okay. So, in the next few lectures, we will be talking about the self-organizing maps. Thank you very much.